Hello, and welcome to my talk about improving carbon emissions of federated large language model interference through classification of task specificity. I'm Geerd-Dietger Hoffmann from Green Coding Solutions, and I wrote this paper together with Verena Majuntke from the HTW in Berlin. So first of all, let me set the frame on what we're going to talk about. So we've got an exponential rise of AI systems in general currently going on. And ChatGPT, sort of being the most dominant, has 180 million active users as of April this year. And only training the fairly small and old compared to nowadays standard models nowadays, produced 500 tons of CO2. And this doesn't include the embodied carbon, so the resources that we use to produce all the chips, the data centers, the racks, networking equipment, and so forth. So we're creating huge amounts of carbon only training these models. And there's been very little research on the impact the interference stage, so the answering phase, has. All major companies are going to miss their self-set CO2 targets because of the rise of AI. And while this is happening, we're in the middle of an existential climate crisis with a very bleak outlook if we continue doing the things we're currently doing. So what is our contribution in this paper? We benchmarked 8 open source LLMs and for their resource usage on a wide variety of different prompts. We created a classifier system, and we then did an empirical measurement to demonstrate that our solution really performs better than the other proposed solutions. When I talk about resource usage or energy usage, in this context, I mean SCI. So initially we used energy as the measurement, and this wasn't very good as different models take different times to answer the prompt, and the energy draw isn't constant in the answering process. So you could have two models, one using the same amount of energy, one using the resource for n seconds and the other one for x seconds. While they still consume the same amount of energy, they use the resource for different amounts of time. And obviously, if you have shorter answering time, you can the utilization of the machine goes up. So we decided to use the SCI. You have to note that the grid intensity we used a constant, and the unit of work is the prompting process, not loading the model into memory or anything, heating up the caches or something. It's basically only the prompt to make this comparable. Also, we use machine energy. We don't use only CPU or REPL or something like that. We use the complete machine. We use the specialized device to measure this. So we also include GPU, CPU, memory, and so forth in the whole value. So how does our system work? We get a prompt. This goes into our classifier, and the classifier then tells us which LLM to route this prompt to. It selects the fittest or most suitable LLM. When I talk about this, it means the LLM that has the highest accuracy gives us basically a correct answer, while having the lowest SCI, using the least resources. So to do this, we selected 5 categories: Python code generation, mathematical understanding, natural language, SQL generation, and translation, whereas translation was German to English. We selected industry-known data sets with high citation count and randomly selected 50 prompts from each category. We then asked or measured 8 open source LLM models. So this gives us 2,000 prompts measured, and then we hand checked if the answers are correct. From each category, we held 5 prompts back for the evaluation stage. So these are the 8 models we selected. We made sure to include different parameter sizes and also different task-specific models. So we really made sure that, for example, we had a translation model in there. The maximum parameter size was 8 billion parameters based on the machine we're doing the measurements on. We couldn't use larger models, unfortunately. So here, as an example, I'm showing the 25 evaluation prompts over the different models with the SCI values. If the answer wasn't correct, we leave the value blank, we delete it. And here you see the matrix basically was prompts on the x-axis and different models on the y-axis, and this will become important later on. What you can see is that for prompt 1, we have hugely different SCI values for the prompts. So Gemma, for example, has 0.6 SCI value, and Tiny Llama has 0.08. So there's a huge difference in SCI while giving the correct answer. What you can also see is that all models perform fairly bad in the math domain. We did some tests with larger models, and the precision increases on larger models. But for the setting we had, this was what we could do. So if you look at accuracy on a per model basis, you can see that Llama is very, very good across the board, whereas Tiny Llama is very good in code generation, being a far smaller model, but not performing as well in SQL generation, for example. And now you can see on the x-axis, the model categories differentiating. So if you look at Llama 3, you can see that code generation has an SCI from 0.3, whereas translation has a 0.09. So there's a huge difference in the model between the different categories or the different tasks it has to perform. Also, there's a huge difference between the different models. So if you look at code generation, you can see that Gemma, for example, has 0.5 an SCI, and Tiny Llama 0.3. So what we saw earlier is true on average on all the prompts we put to the models. So how does our classification process work? So we had the 250 measured prompts per category, and we created embeddings for each of these prompts. We used the MX by embed large model, and we saved the embeddings into a database. And now what happens when we see an unseen prompt is we create an embedding for that prompt. We get the closest known prompt from our database and look into our matrix and basically select the model that has the lowest SCI while still giving us a correct answer. And then we give that prompt to that model for answering. And what we can see is that we have a very, very low SCI score, second to Tiny Llama, so very low, while still having a fairly good accuracy. And our research suggests that if we get more data or more prompts, the accuracy will go up, because currently we're very limited on the 250 sets. That was a time limitation. But research shows that if we have more prompts, the embedding model gets better. So what is the future work? What are we currently working on? We obviously want more prompts and sort of get rid of the category, because the categories don't really matter. It was to show that the models are different. But if we have more prompts, the embedding model will give us the correct or the fittest or the best model. Currently, we only use one-shot prompts. What we want to do is have like a chat interface. Here we also want the possibility of basically trying to lowball an answer in this chat scenario. And if the sentiment of the conversation turns negative, we then give the chat to a better model in a higher accuracy, but these normally then also use more resources. We want to play around with different model sizes. And what we also want to create is a model that can estimate for different LLM models the resources it's going to use to answer a given prompt. Thank you very much for listening. Have a nice day.